Hey there, welcome to some more Precalc talk with yours truly, Miss Wesley. I would start things off with a joke, and actually, I would tell you a steak joke, but they're never really well done. If you want to turn to page 8 of your Polar packet, get ready and get excited about what we get to do today. Today I call kind of just playing around with features and characteristics of polar equations, polar graphs. We're going to use a combo of work on the graphing calculator first, and then a little bit of work on Desmos. I should have that ready too because I want to show you how cool we can make these graphs look. Over the last couple of days, we've been graphing by hand, right? So we've been talking about features of if you had to match a graph to its equation. I don't know if you're familiar enough yet to know off the bat without a calculator which one each of these would be. But if we practice a little bit more, I'm sure you can get pretty confident. I know that A, like an A constant sine or cosine of theta, is going to give you some sort of off-centered circle. And the fact that this is a sine here means that that axis of symmetry, that circle's center, is going to be vertically up from the origin, somewhere around here. So I'm going to go A for option 2 there. Which one of these would be this 4-petal rose? Do you remember if you have an equation of the form A cosine of B theta or A sine of B theta, you get a rose or a flower shape. And if n here is even, right, you're going to have 2n petals. This is a 4-petal rose, and its equation that we can check is from letter C. Well, that leaves this one here. What was this called again? Had a fancy name, limacon, with inner loop. To be number 1, I'll call that option B. It is in the cardioid family. It would be more of a heart shape, a classic heart shape if A and B were the same number here, like a 2 and a 2 or a 5 and a 5. But if A is less than B, it causes that little inner loop to occur. So now what you just might be thinking is, I think it would be a drag to have to graph every single one of these polar equations by hand. Let's experiment using the calculator and Desmos, starting with the calculator. I'm going to write down a few notes for you before we pull the calculator out, first of which is the mode we have to be in, polar mode. Finally, right? Precalc is the class of many modes. We've graphed rectangularly in X and Y. We briefly graphed sequences in series and sequential mode, and then we went to parametric mode for a little bit, but it's time for polar mode. Let me give you a set of steps that'll be good in radians. So I'll put radians as the heading for the column here, and I'm going to make my own column for degree equivalence going next to it. These are just suggestions for your window when you're graphing in polar mode, right? Maybe once around the unit circle will do the trick for a lot of these. So theta minimum 0 and theta max 2 pi is a lot of times sufficient. With a theta step, we'll talk about this in a second, write down pi over 24. Theta step is going to have to do with how smooth the curve is traced out, so this will be a good starting point for us. You don't want to make it too small or too large. In degrees, we could get these equivalents, 0 degrees to 360, all the way around the unit circle, and then this is 7.5 degrees that I decided would be a good starting point for our theta step. So, time to use the calculator. Let me switch over and hit mode first. So I'll go mode, we want to be in polar mode. Where is it? Okay, function mode, parametric, the memories, let's hit enter for polar. Now look at the change. When I go to y equals, hit your y equals, you should see on your graphing calculator a bunch of r equals instead of y. You might have an equation filled in one of these slots. If you do, just go ahead and hit delete. Get rid of it and clear your screen. If you have any plots highlighted, now would be a time to turn them off. Another thing, so let's say I'm jumping to example 1 and I want to graph r equals cosine 2 theta. I wonder if you can predict that this is going to be a rose. So I'll type in cosine, whoops, that didn't work. I'll go y equals cosine, where are you? 2 theta, 2, and theta you're going to find in the same spot where you found x, t for parametric, and n for sequential, but it'll be theta and polar, cosine of 2 theta. Now before hitting graph, let's use our window. Can you hit mode again with me just so I can refresh? I want to be in radian mode for starters. So select radian for mode, and then I'm going to go to window. Do you see that my settings, no one must have graphed in polar mode on this calculator yet before me. If you have different numbers, put these values in now. Do you recognize 0 and then 2 pi, that's 6.28? So 2 pi is your theta max. Theta step, let me just make sure that they default to pi over 24. Let's see, pi over 24 enters that 0.1308997. Mins and maxes for the graphs we're about to do, usually -5 to 5 is sufficient, and if not, I could expand it. I'm going to go -6, let's say, so I have a little bit of extra room to 6 on the x's, skip the scale, and I'll go -6 to 6 on the y's. And now I want to see this rose that should have how many petals? Double 2, it should have 4 petals. I'll hit graph, and you get a nice little tiny version of that rose in blue. Aw, how cute. I want to put this on my picture. Notice that there is no coefficient out in front. There's a silent 1 sitting out front, which means that the petals of the rose are going to span to 1 unit out from the pole. These are rough sketch. So rough sketches, you're not going to actually plot me points like we've been doing the past couple of days. If I ever ask you to sketch one of these, it's just a general picture of it where you're generally having the petals come out to the right length, and I'm not having you do the painstaking process today of plotting all the points yourself. How about 3 cosine of 4 theta? Can we try it? So 3 cosine of 4 theta, this should look a lot cooler. I'll go to y equals. I'm going to clear out the equation that I already had in there, and I'll type in 3 cosine 4 theta. With the same window settings I had before. I'll hit graph, I get a bigger flower. The petals are gonna span out 3 units, and we're gonna do some more things with this graph as well. And there should be double 4 petals. 4 times 2, there should be 8 petals. So this is gonna come out, I'm gonna come out 3 rings roughly, up, down, left, and right. Not my prettiest. And then you gotta fit in a few more petals off to the diagonals to make 8. Okay, so something like that. Now back to my calculator. You may first off not like that this isn't a very symmetric rose, and it should be. Try a zoom with me. Hit zoom square, zoom 5, should just add to the symmetry of this. The circles we graph won't be squashed anymore when we use a zoom square. Does the flower seem like a little too jagged to you? Do you wish it were smoother? Well, we told the calculator to take a point at every 7.5 degrees, or pi over 24. We can change that, but I warn you, don't go crazy with this. Hit window, and I want to change the theta step. Instead of pi over 24, let me make it pi over 48. So pi over 48. I warn you, it's going to take the calculator a little bit longer to graph it, but you get a little smoother of a curve. You will freeze your calculator if you make your theta step too tiny. I'll do one more smaller theta step just for the fun of it. So theta step, let me make it pi over, I'm really nervous about this, 256. It's probably a huge mistake. Hit graph, takes a little bit longer, but look how pretty that rose is. And we could do a lot to this. We could spice this picture up. You want to put, I love how this thing graphs in color. I'll go down to my second R equals, and I'll make it a 4. I'll put 4 cosine and still the 4 theta. And then, I don't know, while I'm at it, let me do a 5 as well. Let me add as a third equation 5 cosine 4 theta. So 4 theta. And now feast your eyes on this. You have the original flower, you have a nice, beautiful, bigger flower, and a third flower outside of it. Now, as we're graphing things, if any of these pictures speak to you, they speak to your artistic passions, jot down the equations to them. We're going to start messing around with some modes and things like that. And if something pops out at you as a recognizable object, I want you to write it down, and I want to know about it because I want to see what creative things you come up with. Now, I'm not done with this one yet. Go back to y equals. Let me not bog the picture down. Let me delete, let me clear out the second and third equations and just go back to this plain graph with, I'll go back to window, and I won't go crazy with the theta step. I'll just do pi over 24 again. Pi over 24. Ooh, something actually, let me clear that out. Something I haven't done. Let's make the theta step bigger and see what that does to this. So what if I just used pi over, what's smaller? How about just every 30 degrees? What if I made the theta step pi over 6? Hit graph and see if what you're about to see is going to trick us. Oh my goodness, what happened to this calculator? Is it trying to lie to me? Do I have more of like a spaceship or a Death Star right now? Because it is the same graph, and do not blame the calculator for this. It's taking points at a lot fewer places around the unit circle. You could get a whole bunch of crazy different graphs by changing this theta step. What was that one, pi over 6? Let me try pi over 3 and see if it gets interesting. So try 60 degrees. I've doubled the theta step, and I get something that doesn't look like it at all. It would be really boring if I just used like a pi over 2. If I just took a point every 90 degrees, the calculator doesn't have much to work with. Only 4 points are going to be graphed, and bam, I get a diamond. Okay, let me go back. Let me go back to a safe, normal theta step. I'll try that standard pi over 24. Now I think I want to move down and try some examples at the bottom of this page. Check out number 4 on page 8 of your packet. It asks you to just graph 0.1 times theta. Imagine what's happening. Imagine graphing r equals theta, right? That means for every theta value you plug in radians or degrees, the radius out from the pole is going to be the same as the measure of the angle. Get what this looks like. Okay, so let me go to my r equals, my y equals. I'll clear out the equation I already have in there. Right now, I'm going to keep the window settings as they just were, and I'm going to type in, as appears in number 4, 0.1 times theta. Okay, get ready for a letdown. Hit graph, and oh man, I don't see that much. Does anybody see a tiny little start to like a snail that's coming out from the origin there? Go to window. This was the same window we used before, -6 to 6, theta min and max. Now notice what's happening. Hopefully your graph looks like the little start to a spiral there, and that's because as r goes up, theta goes up with it. So as the angle increases, the radius is going to go out further and further and further. What do you think I could change on this window? Because remember, I didn't say these numbers were magic numbers that work for everything, but what would make the spiral extend? Well, right now, aren't I limiting myself? I'm just traveling from 0 to 2 pi. Can I go to 4 pi or 8 pi or 12 pi? Let me try 8 pi as my theta max. And I'm going to keep everything else the same and hit graph. And would you look at that? You get a bit more of that spiral as it goes round and round and round. This is an equation you can have a lot of fun with too. I'm going to go back to window. What do you want for a theta max? Can I hear you? You want, I don't know, 10 pi, 20 pi? Let's try, this is a little crazy. Let me go 50 pi. I'll go wild for the theta max. Hit graph, and whoa, do not get dizzy looking at this picture. That's a lot of spiral. This spiral has a special name, and it's a little tricky to graph too. It's a lot tricky to graph. Mine is not going to look beautiful. I'll just draw a spiral coming out from the origin. Again, don't get dizzy. And it's got a special name, spiral of Archimedes. That is any spiral of the form r equals the constant a times theta, r equals a theta. Archimedes was your 3rd century BC Greek mathematician, Archimedes of Syracuse. What I think of when I think of him is the classic Disney movie, one of my top 6, Sword in the Stone. Archimedes was the name of Merlin's owl, if you recall. And the spiral was actually discovered by one of his disciples, a disciple of Archimedes, Conan of Samos. Okay, on to the last one of the page. If we're going to graph this using the TI-84, it's got to be in 2 steps. We've got to square root both sides, and we'll use a positive and a negative version of the square root of 4 cosine of 2 theta. I'm going to go straight back to the calculator and see if we can plot that in 2 steps. So I'll just clear out the equation that we had in there previously. Let's use the positive square root of 4. I really could have snuck out a 2 there. Cosine of 2 theta. I'm still in radian mode, I hope, and I'm still using the same window. We actually don't need 50 pi to be our theta max, so you can change your theta max back to 2 pi for this one. So we'll go theta is 0 to 2 pi. Theta step is still going to be pi over 24. Theta min and max, this is too big. I could go back to a zoom square. I'm going to go like -4 to 4, how about, for the x's, and -4 to 4 for the y's. Okay, and that was just half of what I need to plot, so I'll do the negative square root underneath of it. So negative square root of the same thing, 4 cosine 2 theta, and I'll hit graph and see what it gives me. And you'll see that what we have is pictured as almost a full bow tie or infinity symbol, as I like to call it, but the technical name is a lemniscate. You know what we could change about this to complete the picture? Go to Window. It just needs more theta values in close so it can make that connection. So instead of a theta step of 0.1, let's try a theta step of 0.01. Let's make it really tiny, and I'll hit graph. See how we get closer and closer into that pole using a theta step of 0.01? Again, don't go crazy on this, but I can go Window and maybe make it half of that, go 0.005 and watch it get even closer. So when you sketch this one, it's called a lemniscate. I want you to keep those creative juices flowing, and I will catch you in the next segment. All right, have a great day.